A little late, and I still see people trickling in, but I'm just going to go ahead. My name is Megan Carney. For people who I haven't met before, which is most of you, I've been doing this InfoSec stuff for 10 years or so now. No. All right. I left my Twitter handle up here because if you want to run the queries in these slides and you don't want to type them out by hand, I'm going to post them on my Twitter feed later. All right, so let's get started. Threat hunting, the Macintosh edition. I've seen a lot of threat hunting stuff for Windows. I haven't seen a lot for Macintosh. I think it's something we need to do more of. But before I talk about the Macintosh angle, I want to talk a little bit about why you would do threat hunting at all. And I think the last presentation in that room, Red Team versus Blue Team, was a really good demonstration of this, because even if you have good antivirus, even if you have a really good IDS, even if you've got network sensors running all over, there's still going to be stuff that doesn't match signatures, that's bad, and that's stuff you find by hunting. And the thing with hunting is it's very environment dependent. So I'm going to go over a bunch of queries today. I'm going to talk about a bunch of stuff. You're going to need to look at your own environment and figure out what's normal, because that's why a lot of these things sneak through. We look at our tools and we think they must be covering everything. They're not covering everything. They're covering what they know to be bad because they don't want their customers to get a lot of false positives, right? If you want to define normal for your environment and look for what's abnormal, that's all hunting is. Specifically this presentation, this is a screenshot. I think it's a few months old from threathunting.net. I've highlighted all of those resources there are artifacts that exist only on Windows. So there's a lot of threat hunting resources out there that are not examining what artifacts on Macs look like. And I think this is a real weakness for us, because everybody jokes that Macs don't get malware, even though we know they do, right? But how often are we actually looking on it? Looking for it, and how much of the Mac malware are we finding? I would bet there's a lot of it we're not finding, because we're not looking very hard. So I will be the first to admit that this presentation is just the beginning of the work we need to do as a community. I know Patrick Wardle's been doing some work. I've seen a few other presentations. There's actually a cool conference that's in Hawaii, Objective by the Sea, I think, that's going to come up in a few months, if you happen to be able to go. And we need to do some more work for this. I think we're at the beginning of this work, and I just want to acknowledge that this is not the end of what we need to accomplish. All right, so that's my pep talk. Does that count as a pep talk? I want to talk about my experiment. So I come from an academic background, and I believe in showing your work. What we have here is, sort of an emoji explanation of the work I did. So what I did was I took this Mac Mini, I ran a bunch of malware samples through it, but before I did that, I altered it and I removed the Wi-Fi card. This was so I knew exactly where it could talk out. So if it didn't have an Ethernet cable plugged in and it didn't have the cell phone modem plugged in, I knew it wasn't talking to anything. I had a process monitoring solution installed. If you are familiar with it, you will recognize the screenshots as I go through this presentation. I don't want you to get too hung up on exactly what that process monitoring solution is, because it doesn't matter. If you have any sort of process monitoring solution that's going to record what's executing on your hosts, you can use this research. I used Time Machine to reset between experiments, just because it was built in and it was easy. This, you'll notice, is separate hardware, so there are no virtual machines involved here, which means I didn't have to worry about virtual machine evasion techniques. There are some good things about it, the way this experiment is set up. There are some bad things. I'm going to talk about that more towards the end of the presentation, but this is the environment I was working in. The malware samples, if you are going to do research on Mac malware, I recommend you start with Patrick Wardle's very excellent collection on his site, because he has a lot of samples that are really easy to run. You can search for macOS samples on VirusTotal, and there are a lot of them. However, some of them require, I don't want to get too much in the weeds here. Some of them require being part of an app bundle to run, and unless you know how to build that app bundle, you may have some trouble getting started. I didn't want to mess with it, so I used Patrick Wardle's collection, and it's a very good place to start. Before I move on, if you haven't played with malware before and you're going to start doing this research, please do your homework. Unfortunately, there aren't a lot of, I don't even know of a book that focuses on Mac malware research, but there is a book called Practical Malware Analysis, which is sort of the current Bible for malware analysis. It's got a good overview on how to set up an environment to safely detonate malware and the things you need to worry about. So if you're interested in starting this work, that's where I'd start. But do your homework, or else bad things will happen. So I talked about threat hunting a little bit. I talked about normal versus abnormal. But I want to talk a little bit more about what this experiment was actually trying to achieve. I wasn't trying to find specific indicators. If you want specific indicators, you can get a hash of a file. You can search for specific strings in the file. You can search for network indicators. Where does it call out to? All these things are useful for identifying specific strains of malware. That was not the goal of this experiment. The goal of this experiment was to find the general behavior patterns that indicate badness. Specifically, what does a malicious word process look like on a Mac? There are word macros for a Macintosh. They exist. There's just not many publicly known samples. What does malware do to maintain persistence on a Mac? You know, we know a lot about what it does on Windows. Scheduled tasks, installing in the user's home directory. What does that look like on a Mac? What does malware want to hide? So what are the signs that it tries to erase once it's gaining a foothold? And what does getting a foothold look like? What are they trying to do on the system? What are the system commands they try to run? Where do malware processes and their artifacts live? So a common place to see malware on Windows is in the user's Documents and Settings directory. Nothing typically runs out of the Documents and Settings directory, but users have rights, so you don't need root to install your malware there. What does that look like on a Mac? Since we're running a little bit low on time, I'm going to go over the rest of these questions later. This is basically the outline for my entire presentation. You're going to see a bunch of queries, and I promise I will give you the full index of all the queries at the end. And yeah, we'll talk about some more stuff with that later. So this is a word macro on a Macintosh. You can get the sample from Patrick Wardle's site. It's actually kind of fascinating in that it's very similar to a macro on the Windows side, right? So we have Microsoft Word launching a shell, which launches Python, which launches that PS command. For those of you not familiar with Unix stuff, that lists processes, and then 2 grep commands, and we're going to find out more about what they do later. So this isn't PowerShell, right? But Word doesn't launch Python very often. So this is one of the things you can look for. How would you find this in your environment? You want to look at parent-child relationships. So again, this is a specific process monitoring solution. Don't get too hung up on that. What I want you to recognize is that this solution has IDs that tie parent processes to children. So it all starts with that Microsoft Word and then trickles down to all these other processes. And you can see that grep process there, grep for Little Snitch. If you are familiar with Little Snitch, it's a personal firewall. So what this malware sample is doing is saying, if Little Snitch is present, it's going to find me. So exit. But otherwise, we're going to continue. Oh, and you can see they're using base 64, which is another thing that also happens on the Windows side of the world, except this time they're passing it to Python, because PowerShell is not on Macs. Well, not natively. All right, so how can we detect word macros on a Mac? This is a really simple question. I don't want you to get too wrapped up in the specifics here. This is actually a Splunk query for those of you who know Splunk. But basically what we're asking is, what processes does Word typically launch? And how many of them? Just to set a baseline for your environment. If you have an accounting department that runs a lot of specialized Word documents or spreadsheets, maybe this is going to look different for you. But it will answer the basic question. And what do we see? I love it when you find indicators like this, because a lot of times you start with a hypothesis and you look at the data and it's really messy and complicated and hard to pick out the signal. But this one's pretty simple, right? There's a normal collection of word processes. At most, they're launching 2 processes in the tree. At most. And then we look down here, and this is what abnormal looks like. There's our macro in the center. It's launched, what, 6 processes? And it includes command lines, it includes Python. And if you'll notice in the normal situation, all of those are office binaries. So this is a really simple signal in your environment. If you're looking, just look at what Word normally launches, and then look for variations from that. But you might want to approach this from the opposite direction, right? Maybe instead of investigating an entire fleet of machines, you're investigating one specific machine. And you want to say, I know they opened this weird document, but what did Word run on that machine that wasn't from Word? And that's what this query does. So again, don't get too caught in the weeds. Basically what it's doing is it's saying, look for all the Word processes, and then show me everything that's associated with those processes that's not actually Word. If you are using Splunk, I want to make you aware of a gotcha. Splunk has a number of settings that have to do with making sure one query is not going to kill the cluster for everyone. Basically, it limits the amount of memory that a particular query can use. By default, when you're doing sub-searches, you can only get 10,000 items. So if for some reason you have a machine that ran more than 10,000 instances of Microsoft Word over the time frame you're searching, this is going to have some false negatives. So just watch your time frames and keep an eye on that. But this is what we get. And it's pretty clear, right? Here are the things that Word launched that aren't Word, and you can immediately see that this probably is not a good thing. All right, so we're moving on to persistence. This is the most common, or one of the most common ways to maintain persistence on a Mac. It's sort of equivalent to scheduled tasks. They're called launch agents. They run on boot. They can be installed from the system, by the system in the system directory, or they can be installed on a per user basis. All this command does is it's looking for all the processes that contain launch agents in the path, and then it's going to count them. And you'll notice there's a little bit of fancy regex there because Google Chrome is often installed in the user's home directory. And so if you don't strip out the user's home directory from the path, what you get is a bunch of things that look unique but aren't, because it's basically Chrome, but for each one of your users. So this is something I didn't get to do because of the experiment setup I had. But if you want to run this query regularly, look at using summary indexing or whatever the equivalent is for your sim, because it will make it much more efficient. There are hundreds of launch agents on a Mac before you even install anything. So this is going to return a lot of data. And if you're going to run it over large periods of time, your sim is probably not going to like you very much. So summary indexing or something similar will help. But all of those cautions being said, what do we find? It's really neat how things like this pop out right away. This is XAMloader, which is more crapware than malware, but you probably still want to know if it's on your systems. If you are not familiar with MacKeeper, those names aren't going to jump out at you, but you'll notice the frequency there. It is the only machine in the fleet that has this installed, which is always a red flag and something you want to look out for. What does malware want to hide? This was a really cool result that I was totally not expecting when I started this experiment. And before I talk to you about what the result is, I need to explain something about Apple's internal systems. They have something called a quarantine attribute. It is opt-in, but most well-behaved browsers follow it, which means when you download a file, the file is labeled by the browser as having been downloaded from the internet, where it was downloaded from, what time it was downloaded, and which program downloaded it. This quarantine attribute is of course useful for flagging things that you are going to execute that are downloaded from the internet, which is why, if you're malware, you might want to remove it. This is Ocean Lotus A, nation state malware. I don't remember which nation state. But that command that I've highlighted there, that xadder-d-r, is saying delete the com.apple quarantine from this really weird file, right, that starts with a dot. It's in my home directory, and it's like a really weird executable, right? So what are they doing? They're deleting the quarantine attribute, so it's not flagged by forensics, and so the operating system doesn't flag it when you open it. This command is relatively rare. There are some installers that do it. Chrome updates do it. Again, your mileage may vary in your environment. But the best part of this one is it's really simple to search for. There are no parent-child relationships. There's no frequency counting here. It's just a regex on the command. Of course, you might have to account for some difference in the order of those commands, but it's pretty simple. What does getting a foothold look like? So I noticed with the Mac malware in particular, it seemed to be very busy right when it first got on the system. And so I thought, well, let's look at process trees. How many process trees have a large number of processes in them? And it turns out, not many. I set my threshold at 50. The redacted stuff you see at the bottom there is because when you start doing this research, you will figure out that your internal inventory control system / software deployment system looks a lot like a C2, because it is. It's just yours. So you will probably need to filter some of that out, but this was fairly reliable at finding things like ransomware, right? Because what does ransomware do? It finds a bunch of files, and then it kicks off a process to encrypt every single one of them. And you'll notice this one was really cute. It's using zip internally, which means the encryption key is actually like right there. Doc-A is nation state stuff, but it's showing up here because Doc-A phones home via Tor. If you do not already have Tor installed on your system, Doc-A helpfully installs it for you using Homebrew, which of course kicks off a bunch of processes because it has to download a bunch of packages, and it creates a very busy process tree. I should clarify, what you're seeing here on the command line is the parent process, sort of. It's like the overall process that kicked off all the child processes. So it's not a full list of everything. And especially with that ransomware, you see that's a find command somewhere in there to list all the files that it's going to encrypt. All right, where do malware processes live? This is one of the things I was really interested in, because if you can write a query that says something executing from this directory is bad, it's a really good place to find malware. So the first is processes running from tempters, which is very similar to the Windows side of the world. And this one was actually really cool because I was testing my queries, and this is not my victim machine. This is another machine that I found during the course of my research, and it was Funblor. And so you can see that _update does a few open commands, and then it installs this really weird, like randomly named binary in temp and runs it. So this is something I actually found by accident while I was testing my queries, which is always a good result. Another place that I found malware likes to put itself is library scripts. There's actually not a lot of legitimate stuff that runs out of library scripts, so this is another good place to start. Yeah, I think if I remember correctly, there was some filtering you had to do with this one. But this is, you can see in that window down at the bottom, that snake, and it's a fake Adobe Flash Player. And it's set up that install DP in library scripts. Another thing I noticed that Mac malware tends to do is it sets up a staging area in temp, and then it copies things over to the user's home directory. So if you look for copies that go from temp to the user's home directory, you can find some of this. There's a little bit of noise there, but not a lot. And it's actually a pretty good method. So what you see here is the malware created this __ system directory, which looks super legitimate, right? And then copies it to launch agents. So this is, remember earlier I talked about launch agents and how they can be installed on behalf of the system or per user? It's installing it in the user's directory in this case because that doesn't require root. And it's a launch agent called system, which is now going to run every single time the user logs in. Another thing I noticed that malware likes to do is change own commands. And I'm not sure exactly why this comes up so much, but it did. And if it happens on user directories that start with dots, it's particularly suspicious. This one does have some noise associated with it because there are some, like Git has a preferences directory. There are a few of those things, but it's still relatively good. That's why you see there's that filtering there. And when you see things pop up that are really malicious, they pop out right away, right? Because that is not user-generated activity right there. So this is me filtering. Oh, let's change it. Change mod commands are along a similar line, though this one requires more filtering for some reason. And again, you'll notice you're going to want to filter out the user's home directory at the beginning of it when you're doing your results. One thing I didn't look for, but I thought would be interesting to look at next time, is to look at how many legitimate processes actually do 777 perms. I have a feeling it's not many, but it would be a question worth looking at. All right. So what does C2 look like? Obviously, if you have a network IDS or something like that, or if you're counting bandwidth, you might be able to find really busy C2 that's really noisy. That's not what this command is designed to find. And I apologize, it's a lot of text. But all you need to really know here is it's counting the length of the time the process is running versus how many network connections it's made. So the hypothesis here is if a process is running for a long time, it probably should be making network connections on a regular basis. Otherwise, it's kind of lurking in the background. The reason this query looks complicated is because on this specific platform, the process creation entry and the process ended entry are two different records. So you have to join them to figure out the process time. Which is another good note to make. If for some reason that end of process record doesn't exist, this query might give you false positives. If you shut down a machine unexpectedly, it might not get generated, for instance. But this is the result from that query, which is GrrCON. So here we have a process that's been running for a very long time and has only made one network connection and hasn't done anything else of note. So there's one way you can find command and control. This one's a little bit more complex. That bit I've highlighted there is just a way for you to filter out your internal systems, whatever that means to you. Because as I said, a lot of your internal systems are going to look like command and control and trigger false positives on these queries. What operating systems features does malware use? So a lot of just to take a step back here, a lot of the stuff we're looking at with Mac malware is not, in a broad sense, different than what you see on the Windows side of the world. It's just going to be implemented differently, but those implementations are different when it comes to making detection. So the operating system's features that malware uses are going to be different because of the way it installs persistence. So we talked about launch agents a little bit. After you've installed a launch agent, launch control is what launches it. And one thing I noticed specifically with malware is that if something contains both a shell process and launch control, it's a little suspicious, because what that essentially means is a shell ran launch control, which doesn't happen very often. It's not something users tend to do, and it's not how things happen on boot if it's a launch agent that comes up every time the user logs in. Which one was this? I'm trying to remember which piece of malware this was. Oh, it's right in there. Call me. I think this is a contact information stealer, if I remember right. The other thing that malware tends to do when it has a shell is run lots of those shells to do lots of things. So you can count the number of shells within a process tree, and that can give you some useful results. This particular query, at least on the platform I was using, tends to fall over if you try and run it for more than a small set of hosts. But you could probably play with it and improve that a bit. I've set my threshold at 20, but again, your mileage may vary in your environment. You just need to test and figure out what looks like normal. So here we have another way to find ransomware. And you can see the message, it pops up on the screen. And then we have Ventir, which is something that runs a lot of shells to set up its persistence. What you can see there is that .local directory inside the user's home directory hides a bunch of its artifacts, and it also installs a launch agent, which is one of those shell commands. And, oh yeah, and then it deletes itself. That's that very last shell command for Ventir. All right, cool. I think we're making good time. What does GrrCON look like? Just to take a step back, if you have not studied malware before, a lot of malware comes in to do GrrCON. They want to know where the machine is. They want to know who it belongs to. They want to know what the time zone in it is. And all of that is to figure out how valuable the machine is. I think I have time for a quick detour. So there are lots of places on, I'll call it the dark web for lack of a better term, where you can buy time on computers. So these are computers that somebody else has compromised that you can pay to take over. And there are actually cases where criminals have gotten into a group of machines at a specific company, and it'll be like a deal at the supermarket. Like, we have a bonus today, here are 10 computers at Acme Corporation, and you can gain a foothold on their network and own their company, right? So that's why malware does GrrCON. Of course, it looks a little differently on the Mac. These commands here, just look at the first line of that query. Network setup tells you about the network configuration, of course. Who and who am I will tell you the name of the user the program is running as. And syscontrol will dump a bunch of hardware information about the machine, including some OS information. And so that's super useful information for attackers. Of course, your inventory system is going to be looking at these things too, which is why you have to filter it out. But if you start by looking for process trees that run more than, say, one or two of these commands, it's a fairly reliable way to find malware. You, as a user on the system, might type "who am I" every once in a while, but you're probably not going to type "who am I" and then list all the hardware on your machine and then list all the network interfaces to find out what your IP address is. So here's our results. This is doc A, and doc A is looking for the proxy on the machine so it can configure the proxy to get out. And that top hit is MacSpy, which is basically doing a bunch of hardware reconnaissance to figure out what kind of machine it's on. How does malware try to avoid detection on a Mac? This is where we need to take another little detour. So there's something on the Mac called security off trampoline. And this is basically when you come in as an installer and you want to run with root privileges, but you don't have them, this is how you get them. In most cases, it pops up this little dialog box that you have to enter your password in. And this is, just to be clear here, security off trampoline is a legitimate tool that's used by legitimate installers and illegitimate installers. But I thought it might be interesting to look for rare processes that use it. But before we get there, I'm going to take another little detour. So I talked about malware and how you have to be careful with it. This is what doc-A shows you when it works. So when you're playing with malware, don't trust anything the malware tells you. Make sure you're looking at your artifacts. Make sure you're checking what your monitoring systems are telling you to be sure you know what's going on. Also, I thought this was really cute, so I should share it because this is the only malware sample that I've seen do this. All right, so my hypothesis. If you have a rare process, if you have a process that's used security off trampoline, and there's only, say, one process in your environment that's used it, then maybe that's something to look at. So I specifically looked for the doc-A processes to see how many times they appeared, because some of these are actually system utilities that doc-A is using that are also using security trampoline, so they're not actually, those aren't all malicious hashes. But anyway, it looked good from this point of view. But when I ran the numbers, what I found was lots of hashes are unique over shorter periods of time. So what you have is this conflict, like the more you reduce your window, the easier it is to count, but the more things that look rare that aren't actually rare. The more you increase your window, the better data you get, and the more your SIM tends to fall over on you. So, how can we deal with this problem? Well, I'll get to the deal with part in a moment. This is just some more data to hammer home the point of if a hash was involved in an off-trampoline event, it was probably only reported once by one agent. So the rarity just based on off-trampoline wasn't good enough. What you have to filter on is the rarity in off-trampoline and the rarity in the general population, which led to this unholy query, which, again, try not to get lost in it. Basically, all we're doing is looking for the processes that used off-trampoline, count the number of times it's used, and then add to that information how common is this process in the general population. And then once we have that data, we can filter on it. So that part bolded at the bottom, we're searching for things that are uncommon, and we're searching for things that are uncommon, and we're filtering out things we know that trigger false positives. So it turns out this sort of works, right? So I've highlighted the things that should be rare. Those are those doc-A hits in the red box. But Adobe isn't rare. Why is that showing up? If you noticed, when I clicked past, so if we delve into this a little bit more, what we find is that some of these are rare for this query, but not actually rare in the general population. And the reason for this is I have used a terrible hack. I had to do this because of the platform I was on, because I didn't have summary indexing available to me. But in this Splunk instance, what I could do is I could find the rarest 10,000 hashes and the most common 10,000 hashes, but that left this big chunk in the middle that wasn't categorized at all. So a lot of stuff comes up that's not actually rare. I couldn't solve this problem on the infrastructure I had, but I think you could do this really well with summary indexing, or if you have some sort of known good list. That would also be an awesome way to throw out stuff that you know is false positives. All right. Another thing malware does to hide itself is self-deleting processes. I know this happens on Windows too. Some benign installers do this. So we're going to filter out on common hashes again, and I'm going to use that terrible hack because it's all I have, but it's actually not a bad query. One of the other things you can filter on is, so this is not a commercial, but I'm just going to say it because I'm sure some of you have recognized it now. CrowdStrike, in their data, will actually label the virus total detection count for a hash. They will only alert you if it hits a certain threshold. This makes sense, because some stuff, you know, if it hits 1, probably isn't. You probably don't want that to fire to glass all the time. But particularly if you're doing hunting, maybe that's something you want to look at. So you can add a filter for the virus total count using this query, or whatever you have in your environment. You could, you know, query against virus total and then use that as an optional filter to help get rid of some false positives. One of the other things that malware does to hide itself, and this is true in Windows as well, is orphaned processes. This is super cool. This is CrowdStrike's process tree thing, and you can tell that these look, well, when I looked at them, I could tell that they looked abnormal, because this is not the first process on the system. Launch D is the first process on the system. Everything that happens on the Mac should come down from there. These sort of floating out in the middle of nowhere, that's not how a legitimate process should look, unless you have data missing. But this is not how legitimate processes look. So can we find that using our data? And it turns out you can. Basically, what you do is, again, this query looks complicated, but it's not all that complicated. All we're doing is looking at parent records and joining them to child records. And if the parent doesn't exist, call yourself an orphan. And here we go. This is double robber. And you see that on the bottom? I am an orphan. That's the tag I gave it in this query here. Now, to be precise, what this query does is it looks for parent records in the same time frame as the child record, right? If you have a long-running process, like say an inventory control system that has kicked something off, and it started 10 hours ago and your query is only covering 10 minutes, you're going to get false positives here, and that's why you might need to filter some stuff out. But this is a pretty cool thing to be able to look for through your process data for. All right. If you want to find orphan processes for one host, yeah, I know this one's kind of unholy too, and I'm going to skip over some of the details because I'm running low on time. But this is how you can find them for one host, and these are some of the things I had to filter out. So like application support, the redacted stuff is internal. Yeah. And I promise these will be released, so you do not need to take all this down in your notes. So this was actually pretty good, right? Here are orphan, here are orphaned processes that we found. There were some false positives, but it's not bad. You know, with some research, you could make this a lot better. If we add duration, and that's the duration of the process, and look at virus total count, it gets a lot better. So this is the query running it on one host, looking for orphan processes, and here's what we came up with. All right, so that's the end of my queries. I hope I didn't overwhelm everyone too much. I will be releasing all that text, so now let's talk about just some experiment wrap up. This is what was good about this experiment. The network setup was isolated, which means I didn't have to have a big lab. It talked out on this cell phone connection. The way this particular process monitoring solution works The fact that I was sending data out to this central monitoring server did not name a specific company or person, because lots of companies use that monitoring server. There were no VMs to detect, because there was no virtualization involved. And the process monitoring solution made things easy, mostly. What was not great about this experiment? Malware has been known to change its behavior based on sensing CrowdStrike. So if any of the malware samples I ran was looking for that, they would have changed their behavior. Using hardware does make experiments take longer because your reset time takes longer. Because of that, I had to run multiple samples per experiment, which wasn't great, but you could mostly sort things out because of the process trees. Some of these samples failed to run. Now keep in mind, I had one piece of hardware running one version of the OS with one configuration, right? Some of this code only infects Firefox. Some of it was meant to run on a different architecture or a different version of the OS. None of those are going to run. So here are some improvements that I thought would be fun to investigate. You could configure a Splunk cluster especially for this, so you don't run into so many memory constraints. Using lookup tables instead of joins would be more efficient. If you have some filtering steps that you can't build into the queries, there is an API for Splunk or Elk or whatever sim I'm sure you're using, so you could automate those steps. You can use map. I talked a little bit about summary searches. And this last one I haven't looked at all, but I think would be really fun to look at. It's the equivalent of permissions on your phone, but they exist in the operating system as well on the Macintosh laptops. There's an entitlements database. It's basically the app saying, these are the things I ought to be able to do. And if you were to do a survey of all of the apps in your environment and what they say they ought to be able to do, it might yield some interesting results. All right. So this is the full index of all the queries, and I don't have much time left, but I just want to wrap up by saying I really want somebody in this audience or somebody watching this recording eventually to do more research and to make me look bad and then to tell me about it, because I would love to see more done on this topic, and if you're doing interesting things, please let me know. Yeah, also, I was not here to talk to myself for 45 minutes, so if anyone has questions, I will take them now. All right, cool. You can also find me later if asking questions in large public forums is intimidating.